Hi there, this is Truth Socrates. Welcome to today's video where we are going to do exactly one thing. We are going to graph a function. And here's the function that we're going to graph. It's basically an exponential factor over here, e to the kx something. But we are multiplying it by a linear polynomial, 5x plus 7. Okay? So we are going to try to extract as much information as we can from this function. We're going to do some calculus. We're going to do some maximum, minimum analysis, inflection points, increasing, decreasing, concave up, concave down, all that good stuff. Okay, but first, let's do something simple. Let's just look for intercepts. Okay, here we go. That's a little better. So what happens if we plug in 0 into our function? What's the y-intercept? Okay, so we want f of 0. So 5x is just 0, so that's just 7. E to the minus 0. Okay, so minus 0, of course, is still 0. So we get e to the 0, which is, of course, 1. Okay, so f of 0 is just 7. All right, so that's our y-intercept, 0, comma 7. Is our y-intercept. Okay, now what about x-intercepts? Okay, is there one? Is there more than one? Okay, so we want to know when is the y value, if this whole thing is equal to y, when is that y value equal to 0? Okay, well, we're multiplying two things. So we know that the product of two things is 0 exactly when one of the factors, at least one of the factors, is equal to 0. Okay, so this equals 0 if either 5x plus 7 equals 0 or e to the minus 2/3 x equals 0. Okay, can 5x plus 7 be equal to 0? Sure, x is minus 7 over 5. Okay, so x equals minus 7 over 5 is one possibility. What about this other factor? Can e to the something ever be 0? Well, we said that the range of the exponential function is positive numbers, 0 to infinity. Okay, so this cannot happen. Oops. Okay, so therefore this is the only x-intercept. Okay, so we can write that as minus 7/5, comma 0. That was easy enough. So now let us do some calculus. What are the first and second derivatives? Okay, so we have a product here. We have to apply the product rule. Okay, so if this is u, this is v, then you can get the derivative as u prime times v plus u times v prime. Okay, or you can do it backwards. Okay, so what is, let us put symbols. Okay, so we need the derivative of this times v, which is this, plus u times v prime. Okay, so we'll need this and its derivative. Right. Okay, product rule. Derivative of 5x plus 7, that is simply 5. So we have 5 times e to the minus 2/3 x. And then we have this factor plus 5x times 7. And the derivative of this. Okay, so we know the formula for the derivative of e to the x, e to the u. We just keep the function, and then we take the derivative of what's in the exponent. Okay, so the derivative of minus 2/3 x is simply minus 2/3. Okay, so that's great. That is the first derivative. However, we want to next analyze the sign of the first derivative and ask, okay, when is it 0? Okay, do we have a local max, local min? When is it positive? When is it negative? Okay, that's a little hard to do in the current form of this derivative. Okay, so what we're going to do is we're going to simplify it. Okay, and by that we mean we're going to factor it, right? So you know what? Let me borrow this, steal that a little bit. Okay, there you go. That looks a little better. We have a common factor of e to the minus 2/3 x. Okay, so let's factor that out. Okay, so that will be outside, and then inside, let's bracket this. Okay, whoops, hang on a sec. Okay, don't you just hate it when you delete something you didn't want? There we go. So repaste. Okay, we have a 5 here. And this one also goes outside of the brackets. Okay, so check. We have 5 remaining. This goes out, so we have 5x plus 7. That's minus 2/3 remaining. Okay, but now we want to simplify this, right? So let's take the 1/3 outside. Okay, so we're going to take 1/3 out of that fraction. Okay, which means that this 5 should turn into 15. Okay, and then the negative 2/3 becomes just negative 2. Alrighty, so we're almost there. We just have to simplify what is in the brackets. We get 15 minus 10x, and then 7 times negative 2 minus 14. Okay, so let's make sure. So we get 15 from here. 5x times minus 2 is minus 10x. 7 times minus 2 is minus 14. Oh, wonderful. So we get, in its simplest form, 15 minus 14 is simply 1. 1 minus 10x. Okay, excellent. That's our first derivative, right? So we can see right away where would our critical point be. Okay, so this is 0 when x equals 1/10. 0.1. Okay, what about positive, negative? Okay, so once again, e to the minus 2/3 x is always positive, 1/3 positive. So the sign is completely controlled by 1 minus 10x. Okay, we know it's 0 at 1/10. Okay, which is positive. So what happens if we plug in 0? We're going to get positive 1 here. Positive, positive. It's going to be positive. Okay, so 0 is to the left of 1/10. And at 0, the derivative is positive. So it's going to stay positive to the left of 1/10. Okay, so f prime of x is positive when x is to the left of 1/10. And of course, if you are to the right, you should get something negative. Okay, let's make sure. If we plug in 1 instead, which is to the right of 1/10, you will get 1 minus 10, negative 9 times 1/3, negative 3 times something positive, still negative. Okay, so therefore, our derivative is negative when x is bigger than 1/10. All right. Okay, so we are now ready to take the second derivative of our function. Okay, so we have this as our first derivative, and we are going to apply the product rule once again. So we have a constant here, so we can just leave that out of our derivative. Okay, you don't have to think of it as a triple product. And once again, take the derivative of the first factor, multiply by the second, and then add the first factor times the derivative of the second factor. Okay, so the derivative of the first factor, like before, it's the same factor that we had before. We get e to the minus, we get minus 2/3 times e to the minus 2/3 x. Okay, and we multiply by the second factor. Okay, and then we have the first factor, e to the minus 2/3 x, times the derivative of the second factor, which is minus 10. Okay, great. So now we are going to, again, simplify this second derivative. So the e to the minus 2/3 x, first things first, let's take that outside. So that goes outside, this goes away, and we get just minus 10 for our second contribution here. Okay, now let's take out the 1/3. Fun with fractions. So this now becomes 1/9, and the minus 2/3 just becomes minus 2. But don't forget, we have a minus 10 here, so that turns into minus 30. Okay? So now we get to expand, and what do we get? We get minus 2, and then minus 2 times minus 10x is going to be plus 20x. Okay, minus 30. All right, so check minus 2 plus 20x. Okay, those negatives are always, they're the worst. They are the cause of 99% of computational errors, in my unscientific opinion. Okay, so it looks like we should put the 20x in front. It's positive. And then minus 2 minus 30, minus 32. And that's nice because there's a common factor of 4. So we can simplify it even further. So that becomes now 4 over 9. 20 divided by 4. We have 5x remaining. 32 divided by 4 is 8. Awesome. Okay. So it looks like we have 1 0, and that will happen when x is 8 over 5. This is, whoops, there you go. This is 0 when x is 8 over 5. And what about positive, negative? Okay, so we're going to analyze the second derivative. What happens when you plug in a number less than 8 over 5? Okay, so 0 is less than 8 over 5. When you plug in 0, you get negative 8. Negative times positive, you get negative. So it's going to be negative when x is less than 8 over 5. And if you plug in something bigger than 8 over 5, so how about 2? Okay, just to check. When x is 2, you get 10 minus 8, positive 2, positive, 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 positive. Okay, so it flips. Second derivative is positive when x is greater than 8 over 5. Excellent. So the derivative, the second derivative changes sign at 8 over 5. We get what's called an inflection point. So therefore, thus, x equals 8/5 is an inflection point. Awesome. All right, we're almost ready to graph our function. But my apologies, I forgot to mention one thing. We got this critical point for the first derivative, and we saw that the first derivative was positive when x is smaller than this critical point, and negative when it's bigger. Okay, so it is, your function is increasing to the left. Okay, I should use my right hand because you're looking this way. Your function is increasing to the left of 1/10, and then it becomes decreasing to the right of 1/10. So therefore, this critical point should be a local maximum point. Okay, so we want the y-coordinates of that point, and we also want it for our inflection point. Okay, so plug in the two numbers. Okay, so this is a copy of our function. What happens when you plug in 1/10? Okay, so f of 1/10, our local maximum. 5 over 10 is 1/2. Okay, so 7.5. E to the minus 2/3 of 1/10, 2 over 30, or 1 over 15. Okay, So let's see if Maple will compute this for us. I do believe I have some invisible characters there. Oh yeah, it's fine with it. So it's about 7.016, and now we will do it for 8/5. 8/5. Okay, 8/5. How convenient that is just 8. And then times minus 8/5, so that's minus 16/5 times 3, 15. Okay, just about -1. Okay, so is Maple gonna be nice to... Yeah, all right. So it's about 5.162. Okay, I'm gonna write those down and then we'll go to Maple and plug in these points. Okay, so we have used GeoGebra many times to graph functions for us. And yeah, at the end of our work, we will graph the original function and see how close we are to what we're going to do next. So, but first, let's plug in the points or plot the points that we have. Okay, so we know that the y-intercept is 0, 7. Okay, and then the x-intercept is minus 7/5. 0. Okay, so those are, whoops, what is that? Minus 7/5. Okay, let's just start over, delete. Minus 7/5, and then comma, 0. I always have to get out of the environment. Okay, there we go. We have a local maximum at 1/10. Okay, so it's close to 0, unfortunately. 0.1, 1/10, and then 7.0163. Okay, so these 2 points are really close to each other. Okay, so we have to kind of zoom in there to see that, yeah, of course, it has to be, it's local maximum, so it better be higher than the y-intercept. Okay, but you can barely tell them apart. Okay, and we have an inflection point, 8/5, and then, okay, here we go again, 5.16. Okay, there we go. That's nice. So that's separated from those 2 points, which are close together. Okay, so let's think about the rest of the graph. Okay, so I know that you can see my cursor as a fuzzy yellow dot. Okay. We know that to the left of the local maximum, our function is increasing, and then to the right, it is decreasing. Okay, so it should be something like that. But now let's think about concavity. Okay, this is the inflection point. To the left, it was concave down. So concave down looks like this. Okay, so increasing and concave down, decreasing, still concave down. Okay, now it's going to be concave up, so it's going to look like this. Now, can we cross the x-axis once again? No, that's not going to be possible anymore because we only have one x-intercept. We have exactly one x-intercept. Okay, so yeah, we don't have a lot of data to the right of this inflection point. Okay, so before we graph the function, let's go back to our work area and let's plot a couple of points. Okay, so let's see what happens if we plug in maybe 4 and then maybe 8. What is happening to our function? Okay, so let's plug in 4 and we'll plug in 8. And here we'll put 8. Okay, so 5 times 4 is 20, 27. Okay, but plug in 4, so that's going to be minus 8/3. Okay. Oh, Maple, what is the answer? 1.876. Okay, so it's going down. It has to be because it's decreasing. Still concave up. Okay, 8. So we get 47. And then minus 32/3. 8 times, oh, I'm sorry, 8 times is 16. I double dipped. All right, yes, minus 16 over 3. Okay, what is that? It's about 0.22. Ooh, it got smaller, a lot smaller. Okay, so now this makes me curious. What if we go a little further? Let's go to 16. Okay, so 16 times 5 is 80. We're going to get 87 now. 16 times 2 minus 32 over 3. All right, so what are we going to get? Let's erase that. And we get, 10 to the minus 3, 2.027. Ooh, that's a really small number. Okay, so now let's put our thinking caps on. What's going on here? So remember that our function has an exponential function multiplied by a polynomial, linear factor, okay? If we ignore this, okay, take that away. We know that this is an exponential function. Its coefficient, the coefficient of x is negative, okay? Which means that it is a decreasing function, and you have a horizontal asymptote towards positive infinity, okay? But you do have that 5x plus 7, which we cannot ignore, okay? Let's be honest now. After all, if we plug in a good-sized number, 16, we get 87. That's a big number, but this appears to be overpowering that 87. Okay, let's just take a look at that factor by itself. Okay, what are you approximately? You are about, yeah, it's pretty small. Very small, 10 to the minus 5. Okay, so that's what, 4 zeros followed by a 2, whatever. Okay, it's really, really small. Even if you multiply it by 87, it's still small. Okay, you have 3 zeros followed by a 2. Okay, so what's happening here? Your function has a horizontal asymptote. Okay, we're approaching the x-axis just like e to the minus 2/3 x would approach the x-axis as we go to plus infinity. And we are approaching it from above because this factor is positive. Okay, in a little bit, we're going to be we will show you that this limit is exactly 0 as x goes to infinity. Okay, so right now, we're just looking at some hopefully convincing numerical data showing that we should have a horizontal asymptote as x goes to plus infinity. All right, so let's put in those 3 points. We have 4, 1.876. All right, and then we did 8, 0.227, and 16, which is to the right. So are we going to see it? Let's shrink it a little bit. There we go. So we have 16. Whoops. Let's just delete that part. Delete, and we get 16, 0.002. Okay, so yeah, you can barely tell it apart from the x-axis. Okay, so one more time. Okay, how are we going to draw our function? Okay, so we're going to pretend that our cursor is an actual pen. I don't want to ruin our beautiful plotted points. So we're going to go up, 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 up. Y-intercept, local maximum right next to it. Okay, now we go down, still concave down. Now we go concave up. Okay, and we're going to hit these 3 accessory points. Okay, so they're not local max, they're not local min. They're just extra points for us to draw our function. Okay, so now let's make it official. Let us plot the function. F of x is 5x plus 7 times e to the negative 2/3 x minus 2x over 3. Oh, okay, so there you go. Okay, so that is the correct graph of our function. Okay, so there you go. There's our example. Hope you enjoyed the video. And until the next time that we see each other, I hope you enjoyed the rest of your day. See you soon.